Chapter 1: The Machine Learning Landscape. Not so long ago, if you had picked up your phone and asked its way home, it would have probably ignored you, and people would have questioned your sanity. But machine learning is no longer science fiction. Billions of people use it every day. And the truth is, it has actually been around for decades in some specialized applications, such as optical character recognition. The first machine learning application that really became mainstream, improving the lives of hundreds of millions of people, took over the world back in the 1990s, the spam filter. It's not exactly a self-aware robot, but it does technically qualify as machine learning. It has actually learned so well that you seldom need to flag an email as spam anymore. It was followed by hundreds of machine learning applications that now quietly power thousands of products and features that you use regularly: voice prompts, automatic translation, image search, product recommendations, and many more. Where does machine learning start and where does it end? What exactly does it mean for a machine to learn something? If I download a copy of all Wikipedia articles, has my computer really learned something? Is it suddenly smarter? In this chapter, I will start by clarifying what machine learning is and why you may want to use it. Then, before we set up to explore the machine learning continent, we will take a look at the map and learn about the main regions and the most notable landmarks. Supervised versus unsupervised learning and their variants, online versus batch learning, instance-based versus model-based learning. Then we will look at the workflow of a typical machine learning project, discuss the main challenges you may face, and cover how to evaluate and fine-tune a machine learning system. This chapter introduces a lot of fundamental concepts and jargon that every data scientist should know by heart. It will be a high-level overview. It's the only chapter without much code. All rather simple, but my goal is to ensure everything is crystal clear to you before we continue on to the rest of the book. So grab a coffee and let's get started. Machine learning is a science, an art of programming computers so they can learn from data. Here's a slightly more general definition, and a more engineering-oriented one. Your spam filter is a machine learning program that, given examples of spam emails flagged by users, and examples of regular emails, non-spam, also called ham, can learn to flag spam. The examples that the system uses to learn are called a training set. Each training example is called a training instance, or sample. The part of a machine learning system that learns and makes predictions is called the model. Neural networks and random forest are examples of models. In this case, the task T is to flag spam for new emails, the experience E is the training data, and the performance measure P needs to be defined. For example, you can use the ratio of correctly classified emails. This particular performance measure is called accuracy, and it is often used in classification tasks. If you just download a copy of all Wikipedia articles, your computer has a lot more data, but this is not suddenly better at any task. This is not machine learning. Consider how you would write a spam filter using traditional programming techniques. First, you would examine what spam typically looks like. You might notice that some words or phrases, such as for you, credit card, free, and amazing, tend to come up a lot in the subject line. Perhaps you would also notice a few other patterns in the sender's name, the email's body, and other parts of the email. You would write a detection algorithm for each of the patterns that you noticed, and your program would flag emails as spam if a number of these patterns were detected. You would test your program and repeat steps 1 and 2 until it was good enough to launch. Since the problem is difficult, your program will likely become a long list of complex rules, pretty hard to maintain. In contrast, a spam filter based on machine learning techniques automatically learns which words and phrases are good predictors of spam by detecting unusually frequent patterns of words in the spam examples compared to the ham examples. The program is much shorter, easier to maintain, and most likely more accurate. What if spammers notice that all their emails containing "for you" are blocked? They might start writing "for you" instead. The spam filter using traditional programming techniques would need to be updated to flag "for you" emails. If spammers keep working around your spam filter, you would need to keep writing new rules forever. In contrast, a spam filter based on machine learning techniques automatically notices that "for you" has become unusually frequent in spam flagged by users, and it starts flagging them without your intervention. Another area where machine learning shines is for problems that either are too complex for traditional approaches or have no known algorithm. For example, consider speech recognition. Say you want to start simple and write a program capable of distinguishing the words 1 and 2. You might notice that the word 2 starts with a high-pitched sound T. So you could hardcode an algorithm that measures high-pitched sounds intensity and use it to distinguish ones and twos, but obviously this technique will not scale to thousands of words spoken by millions of very different people in noisy environments and in dozens of languages. The best solution, at least today, is to write an algorithm that learns by itself, given many example recordings for each word. Finally, machine learning can help humans learn. Machine learning models can be inspected to see what they have learned, although for some models this can be tricky. For example, once the spam filter has been trained on enough spam, it can easily be inspected to reveal the list of words and combinations of words that it believes are the best predictors of spam. Sometimes this will reveal unsuspected colorations or new trends, and thereby lead to a better understanding of the problem. Digging into large amounts of data to discover hidden patterns is called data mining, and machine learning excels at it. To summarize, machine learning is great for problems for which existing solutions require a lot of fine-tuning or long lists of rules. A machine learning model can also often simplify code and perform better than the traditional approach. Complex problems for which using a traditional approach yields no good solution. The best machine learning techniques can perhaps find a solution. Fluctuating environments, a machine learning system can easily be retrained on new data, always keeping it up to date. Getting insights about complex problems, large amounts of data. Let's look at some concrete examples of machine learning tasks, along with the techniques that can tackle them. Analyzing images of products in a production line to automatically classify them. This is image classification, typically performed using convolutional neural networks, CNN, or sometimes transformers. Detecting tumors in brain scans. This is semantic image segmentation, where each pixel in the image is classified as we want to determine the exact location and shape of tumors, typically using CNNs or transformers. Automatically classifying news articles. This is natural language processing, NLP, and more specifically text classification, which can be tackled using recurrent neural networks, RNNs, and CNNs, but transformers work even better. Automatically flagging offensive comments in discussion forums. This is also text classification using the same NLP tools. Summarizing long documents automatically. This is a branch of NLP called text summarization, again using the same tools. Creating a chatbot or a personal assistant. This involves many NLP components, including natural language understanding, NLU, and question answering modules. Forecasting your company's revenue next year based on many performance metrics. This is a regression task, predicted values. They may be tackled using any regression model, such as linear regression or polynomial regression model, a regression support vector machine, a regression random forest, or an artificial neural network. If you want to take into account sequences of past performance metrics, you may want to use RNNs, CNNs, or transformers. Making your app react to voice commands. This is speech recognition, which requires processing audio examples. Since they are long and complex sequences, they are typically processed using RNNs, CNNs, or transformers. Detecting credit card fraud. This is anomaly detection, which can be tackled using isolation forest, Gaussian mixture models, or autoencoders. Segmenting clients based on their purchases so that you can design a different marketing strategy for each segment. This is clustering, which can be achieved using k-means, DBS scan, and more. Representing a complex high-dimensional dataset in a clear and insightful diagram. This is data visualization, often involving dimensionality reduction techniques. Recommending a product that a client may be interested in based on past purchases. This is a recommender system. One approach is to feed past purchases and other information about the client to an artificial neural network and get it to output the most likely next purchase. This neural net would typically be trained on past sequences of purchases across all clients. Building an intelligent bot for a game. This is often tackled as in reinforcement learning, which is the branch of machine learning that trains agents, such as bots, to pick the actions that will maximize their rewards over time. A bot may get a reward every time the player loses some life points within a given environment, such as the game. The famous AlphaGo program that beat the world champion at the game of Go was built using reinforcement learning. This list could go on, but hopefully it gives you a sense of the incredible breadth and complexity of the task that machine learning can tackle and the types of techniques that you would use for each task. There are so many different types of machine learning systems that it is useful to classify them in broad categories based on the following criteria. How they are supervised during training, supervised, unsupervised, semi-supervised, self-supervised, and others. Whether or not they can learn incrementally on the fly, online versus batch learning. Whether they work by simply comparing new data points to known data points, or instead by detecting patterns in the training data and building a predictive model, much like scientists do. Instance-based versus model-based learning. These criteria are not exclusive. You can combine them in any way you like. For example, A state-of-the-art spam filter may learn on the fly using a deep neural network model trained using a human-provided examples of spam and ham. This makes it an online, model-based, supervised learning system. Let's look at each of these criteria a bit more closely. Machine learning systems can be classified according to the amount and type of supervision they get during training. There are many categories, but we'll discuss the main ones: supervised learning, unsupervised learning, self-supervised learning, semi-supervised learning, and reinforcement learning. In supervised learning, the training set you feed to the algorithm includes the desired solutions, called labels. A typical supervised learning task is classification. The spam filter is a good example of this. It is trained with many example emails along with your class, spam or ham, and it must learn how to classify new emails. Another typical task is to predict the target numeric value, such as the price of a car, given a set of features, mileage, age, brand, etc. This sort of task is called regression. To train the system, you need to give it many examples of cars, including both their features and their targets, their prices. Note that some regression models can be used for classification as well, and vice versa. For example, logistic regression is commonly used for classification as it can output a value that corresponds to the probability of belonging to a given class, 20% chance of being spam. In unsupervised learning, as you might guess, the training data is unlabeled. The system tries to learn without a teacher. For example, say you have a lot of data about your blog's visitors. You may want to run a clustering algorithm to try to detect groups of similar visitors. At no point do you tell the algorithm which group a visitor belongs to. It finds those connections without your help. For example, you might notice that 40% of your visitors are teenagers who love comic books and generally read your blog after school, while 20% are adults who enjoy science fiction and who visit during the weekends. If you use a hierarchical clustering algorithm, it may also subdivide each group into smaller groups. This may help you target your post for each group. Visualization algorithms are also good examples of unsupervised learning. You feed them a lot of complex and unlabeled data, and they output a 2D or 3D representation of your data that can easily be plotted. These algorithms try to preserve as much structure as they can, trying to keep separate clusters in the input space from overlapping the visualization, so that you can understand how the data is organized and perhaps identify unsuspected patterns. A related task is dimensionality reduction, in which the goal is to simplify the data without losing too much information. One way to do this is to merge several correlated features into one. For example, a car's mileage may be strongly correlated with its age, so that the dimensionality reduction algorithm will merge them into one feature that represents the car's wear and tear. This is called feature extraction. Yet another important unsupervised task is anomaly detection. For example, detecting unusual credit card transactions to prevent fraud, catching manufacturing defects, or automatically removing outliers from a dataset before feeding it to another learning system. The system shows mostly normal instances during training, so it learns to recognize them. Then, when it sees a new instance, it can tell whether it looks like a normal one or whether it is likely an anomaly. A very similar task is anomaly detection. It aims to detect new instances that look different from all instances in the training set. This requires having a very clean training set, devoiding of any instance you would like the algorithm to detect. For example, if you have thousands of pictures of dogs and 1% of these pictures represent chihuahuas, then a novelty detection algorithm should not treat new pictures of chihuahuas as novelties. On the other hand, anomaly detection algorithms may consider these dogs as so rare and so different from other dogs that they would likely classify them as anomalies, no offense to chihuahuas. Finally, another common unsupervised task is association rule learning, in which the goal is to dig into large amounts of data and discover interesting relations between attributes. For example, suppose you own a supermarket. Running an association rule on your sales logs may reveal that people who purchase barbecue sauce and potato chips also tend to buy steak. Thus, you may want to place these items close to one another. Since labeling data is usually time-consuming and costly, you will often have plenty of unlabeled instances and few labeled instances. Some algorithms can deal with data that's particularly labeled. This is called semi-supervised learning. Some photo hosting services, such as Google Photos, are good examples of this. Once you upload all your family photos to the service, it automatically recognizes that the same person A shows up in photos 1, 5, and 11, while another person V shows up in photos 2, 5, and 7. This is the unsupervised part of the algorithm, clustering. Now, all the system needs is for you to tell it who these people are. Just add one label per person and it is able to name everyone in every photo, which is useful for searching photos. Most semi-supervised learning algorithms are combinations of unsupervised and supervised algorithms. For example, a clustering algorithm may be used to group similar instances together, and then every unlabeled instance can be labeled with the most common label in its cluster. Once the whole dataset is labeled, it is possible to use any supervised learning algorithm. Another approach to machine learning involves actually generating a fully labeled dataset from a fully unlabeled one. Again, once the whole dataset is labeled, any supervised learning algorithm can be used. This approach is called self-supervised learning. For example, if you have a large dataset of unlabeled images, you can randomly mask a small part of each image and then train the model to recover the original image. During training, the mask images are used as the inputs to the model, and the original images are used as the labels. The resulting model may be quite useful in itself. For example, to repair damaged images or to erase unwanted objects from pictures. But more often than not, a model trained using self-supervised learning is not the final goal. You usually want to tweak and fine-tune the model for a slightly different task, one that you can actually care about. For example, suppose that what you really want is to have a pet classification model. Given a picture of any pet, it will tell you what species it belongs to. If you have a large dataset of unlabeled photos of pets, you can start by training an image repairing model using self-supervised learning. Once it's performing well, it should be able to distinguish different pet species. When it repairs an image of a cat whose face is masked, it must know not to add a dog's face. Assuming your model's architecture allows it, and most neural networks architectures do, it is then possible to tweak the model so it predicts pet species instead of repairing images. The final step consists of fine-tuning the model on a labeled dataset. The model already knows what cats, dogs, and other pet species look like, so this step is only needed so the model can learn the mapping between the species it already knows and the labels we expect from it. Some people consider self-supervised learning to be a part of unsupervised learning, since it deals with fully unlabeled datasets. But self-supervised learning uses generated labels during training, so in that regard, it's closer to supervised learning. And the term unsupervised learning is generally used when dealing with tasks like clustering, dimensionality reduction, or anomaly detection, whereas self-supervised learning focuses on the same task as supervised learning, mainly classification and regression. In short, it's best to treat self-supervised learning as its own category. Reinforcement learning is a very different beast. The learning system, called an agent in this context, can observe the environment, select and perform actions, and get rewards in return. It must then learn by itself what is the best strategy, called a policy, to get the most reward over time. A policy defines what action the agent should choose when it is in a given situation. For example, many robots implement reinforcement learning algorithms to learn how to walk. DeepMind's AlphaGo program is also a good example of reinforcement learning. It made the headlines in May 2017 when it beat KG, the #1 ranked player in the world at the time, at the game of Go. It learned its winning policy by analyzing millions of games and then playing many games against itself. Note that learning was turned off during the games against the champion. AlphaGo was just applying the policy it had learned. As you will see in the next section, this is called offline learning. Another criterion used to classify machine learning systems is whether or not the system can learn incrementally from a stream of incoming data. In batch learning, the system is incapable of learning incrementally. It must be trained using all the available data. This will generally take a lot of time and computing resources, as typically done offline. First, the system is trained, and then it is launched into production and runs without learning any more. It just applies what it has learned. This is called offline learning. Unfortunately, a model's performance tends to decay slowly over time simply because the world continues to evolve while the model remains unchanged. This phenomenon is often called model rot or data drift. The solution is to regularly retrain the model on up-to-date data. How often you need to do that depends on the use case. If the model classifies pictures of cats and dogs, its performance will decay very slowly, but if the model deals with fast-evolving systems, for example making predictions of the financial market, then it is likely to decay quite fast. If you want a batch learning system to know about new data, such as a new type of spam, you need to train a new version of the system from scratch on the full dataset, not just the new data but also the old data, then replace the old model with the new one. Fortunately, the whole process of training, evaluating and launching a machine learning system can be automated fairly easy. So even a batch learning system can adapt to change. Simply update the data and train a new version of the system from scratch as often as needed. This solution is simple and works fine. The training using the full set of data can take many hours, so you would typically train a new system only every 24 hours or even just weekly. If your system needs to adapt rapidly changing data to predict stock prices, then you need a more reactive solution. Also, training on the full set of data requires a lot of computer resources: CPU, memory space, disk input-output, network input-output, etc. If you have a lot of data and you automate your system to train from scratch every day, it will end up costing you a lot of money. If the amount of data is huge, it may even be impossible to use a batch learning algorithm. Finally, if your system needs to be able to learn autonomously and it has limited resources, a smartphone applications or a rover on Mars, then carrying around large amounts of training data and taking up a lot of resources to train for hours every day is a showstopper. A better option in all these cases is to use algorithms that are capable of learning incrementally. In online learning, you train the system incrementally by feeding it data instances sequentially, either individually or in small groups called mini batches. Each learning step is fast and cheap, so the system can learn about new data on the fly as it arrives. Online learning is useful for systems that need to adapt to change extremely rapidly to detect new patterns in the stock market. It's also a good option if you have limited computer resources, for example, if the model is trained on a mobile device. Additionally, online learning algorithms can be used to train models on huge datasets that cannot fit in one machine's main memory. This is called out-of-core learning. The algorithm loads part of the data, runs a training step on that data, and repeats the steps until it has run on all of the data. One important parameter of online learning systems is how fast they should adapt to changing data. This is called the learning rate. If you set a high learning rate, then your system will rapidly adapt to new data, but it will also tend to quickly forget the old data. And you don't want a spam filter to flag only the latest kinds of spam it was shown. Conversely, if you set a low learning rate, the system will have more inertia. That is, it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequences of non-representative data points, outliers. A big challenge with online learning is that if bad data is fed to the system's performance will decline, possibly quickly, depending on the data quality and learning rate. If it's a live system, your clients will notice. For example, bad data could come from a bug, malfunctioning sensor on a robot, or it could come from someone trying to game the system, spamming a search engine to try to rank high in search results. To reduce this risk, you need to monitor your system closely and promptly switch learning off and possibly revert to a previously working state if you detect a drop in performance. You may also want to monitor the input data and react to abnormal data, for example using an anomaly detection algorithm. One more way to categorize machine learning systems is by how they generalize. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to make good predictions for generalized to examples it has never seen before. Having a good performance measure on the training data is good, but insufficient. The true goal is to perform well on new instances. There are two main approaches to generalization: instance-based learning and model-based learning. Possibly the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have been already being flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your email filter could be programmed to also flag emails that are similar to known spam emails. This requires a measure of similarity between two emails. A very basic similarity measure between two emails could be to count the number of words they have in common. The system would flag an email as spam if it has many words in common with a known spam email. This is called instance-based learning. The system learns the examples by heart, then generalizes to new cases by using similarity measure to compare them to the learned examples, or a subset of them. For example, in figure 116, the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. Another way to generalize from a set of examples is to build a model of these examples, then use that model to make predictions. This is called model-based learning. For example, suppose you want to know if money makes people happy. So you download the Better Life Index data from the OECD's website and the World Bank stats about gross domestic product per capita. Then you join the tables and sort by GDP per capita. Table 1.1 shows an excerpt of what you get. Let's plot the data for these countries. There does seem to be a trend here. Although the data is noisy, partially random, it looks like life satisfaction goes up more or less linearly as the country's GDP per capita increases. So you decide to model life satisfaction as a linear function of GDP per capita. This step is called model selection. You selected a linear model of life satisfaction with just one attribute, GDP per capita. This model has two model parameters, theta null and theta 1. By tweaking these parameters, you can make your model represent any linear function, as shown in figure 119. Before you can use your model, you need to define the parameters value theta null and theta 1. How can you know which values will make your model perform best? To answer this question, you need to specify performance measure. You can either define a utility function or fitness function that measures how good your model is, or you can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training examples. The objective is to minimize this distance. This is where the linear regression algorithm comes in. You feed it to your training examples and it finds the parameters that make the linear model fit best to your data. This is called training the model. In our case, the algorithm finds that the optimal parameters value are theta null equals 3.75 and theta 1 equals 6.78 times 10 to the power of minus 5. Now the model fits the training data as closely as possible for a linear model, as you can see in figure 1.20. We're finally ready to run the model to make predictions. For example, say you want to know how happy Cypriots are, and the OECD data does not have the answer. Fortunately, you can use the model to make a good prediction. If you look up Cyprus GDP per capita, find $37,655, and then apply your model and find that life satisfaction is likely to be somewhere around 3.75 plus 37,655 times 6.78 times 10 to the power of minus 5, which is equal to 6.30. To whet your appetite, example 1.1 shows the Python code that loads the data, separates the input x from the labels y, creates a scatter plot for visualization, and then trains a little model and makes a prediction. If all went well, your model will make good predictions. If not, you may need to use more attributes, employment rate, health, air pollution, etc., get more or better quality training data, or perhaps select a more powerful model, polynomial regression model. In summary, you study the data, you select the model, you train it on the training data, the learning algorithm search for model parameters values that minimize the cost function. Finally, you apply the model to make predictions in new cases. This is called inference, hoping that this model will generalize well. This is what a typical machine learning project looks like. In chapter 2, you will experience this firsthand by going through a project end to end. We have covered a lot of ground so far. Now you know what machine learning is really about, why is it useful, what some of the most common categories of machine learning systems are, and what a typical project workflow looks like. Now, let's look at what can go wrong in learning and prevent you from making accurate predictions. In short, since your main task is to select a model and train it on some data, these two things can go wrong and are bad model and bad data. Let's start with examples of bad data. For a toddler to learn what an apple is, all it takes is for you to point to an apple and say, apple, possibly repeating this procedure a few times. Now the child is able to recognize apples in all sorts of colors and shapes. Genius. Machine learning is not quite there yet. It takes a lot of data for most machine learning algorithms to work properly. Even for very simple problems, you typically need thousands of examples. And for complex problems such as image or speech recognition, you may need millions of examples, unless you can reuse parts of an existing model. In order to generalize well, it is crucial that your training data be representative of the new cases you want to generalize to. This is true whether you use instance-based learning or model-based learning. For example, the set of countries you used earlier for training the linear model was not perfectly representative. It did not contain any country with a GDP capita lower than 23,500 or higher than 62,500. Figure 122 shows what the data looks like when you add such countries. If you train a linear model on this data, you get the solid line, while the L model is represented by the dotted line. As you can see, not only does adding a few missing countries significantly alter the model, but it makes it clear that such a simple linear model is probably never going to work well. It seems that very rich countries are not happier than moderately rich countries. In fact, they seem slightly unhappier. And conversely, some poor countries seem happier than many rich countries. By using a non-representative training set, you train a model that is unlikely to make accurate predictions, especially for very poor and very rich countries. It is crucial to use a training set that is representative of the cases you want to generalize to. This is often harder than it sounds. If the example is too small, you will have sampling noise, non-representative data as a result of chance, but even very large samples can be non-representative if the sampling method is flawed. This is called sampling bias. Obviously, if your training data is full of errors, outliers, and noise due to poor quality measurements, it will make it harder for the system to detect the underlying patterns, so your system is less likely to perform well. This is often well worth the effort to spend time clearing up your training data. The truth is, most data scientists spend a significant part of the time just doing just that. The following are a couple examples of when you'd want to clean up training data. If some instances are clearly outliers, it may help to simply discard them or try to fix the errors manually. If some instances are missing a few features, 5% of your customers did not specify their age, You must decide whether you want to ignore this attribute altogether, ignore these instances, filling the missing values with the medium age, or train one model with a feature and one model without it. As the saying goes, garbage in, garbage out. Your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant ones. A critical part of success of a machine learning project is coming up with a good set of features to train on. This process, called feature engineering, involves the following steps: feature selection, selecting the most useful features to train on among existing features; feature extraction, combining existing features to produce a more useful one, as we saw earlier, dimensionality reduction algorithms can help; creating new features by gathering new data. Now that we have looked at many examples of bad data, let's look at a couple of examples of bad algorithms. Say you're visiting a foreign country and a taxi driver rips you off. You might be tempted to say that all taxi drivers in that country are thieves. Overgeneralizing is something that we humans do all too often, and unfortunately machines can fall into the same trap if we are not careful. In machine learning, this is called overfitting. It means that the model performs well in the training data, but it does not generalize well. Figure 123 shows an example of a high-degree polynomial life satisfaction model that strongly overfits the training data. Even though it performs much better on the training data than the simple linear model, would you really trust its predictions? Complex models such as deep neural networks can detect subtle patterns in the data, but if the training set is noisy, or if it's too small, which introduces sampling noise, then the model is likely to detect patterns in the noise itself, as in the taxi driver example. Obviously, these patterns will not generalize to new instances. For example, say you feed your life satisfaction model many more attributes, including uninformative ones such as the country's name. In that case, a complex model may detect patterns like the fact that all countries in the training data with a W in their name have a life satisfaction greater than 7. New Zealand, Norway, Sweden, and Switzerland. How confident are you that the W satisfaction rule generalizes to Rwanda or Zimbabwe? Obviously, this pattern occurred in the training data by pure chance, but the model has no way to tell whether a pattern is real or simply a result of noise in the data. Constraining the model to make it simpler and reduce the risk of overfitting is called regularization. For example, the linear model we defined earlier has two parameters, theta null and theta 1. This gives the learning algorithm 2 degrees of freedom to adapt the model to the trained data. It can tweak both the height, theta null, and the slope, theta 1, of the line. If we force theta 1 equals 0, the algorithm would have only 1 degree of freedom and it would have a much harder time fitting data properly. All it could do is move the line up or down to get as close as possible to the training instances, so it would end up around the mean. A very simple model indeed. If we allow the algorithm to modify theta 1 but we force it to keep it small, then the learning algorithm would effectively have somewhere in between 1 and 2 degrees of freedom. It would produce a model that's simpler than one with 2 degrees of freedom, but more complex than one with just 1. You want to find the right balance between fitting the training data perfectly and keeping the model simple enough to ensure that it will generalize well. Figure 124 shows 3 models. The dotted line represents the original model that was trained on the countries represented as circles, with all the countries represented as squares. The solid line is our second model trained with all countries, circles and squares, and the dashed line is a model trained with the same data as the first model but with a regularization constraint. You can see that regularization forced the model to have a smaller slope. This model does not fit the training data, circles, as well as the first model, but it actually generalizes better to new examples that it did not during training, squares. The amount of regularization to apply during learning can be controlled by a hyperparameter. A hyperparameter is a parameter of a learning algorithm, not of the model. As such, it is not affected by the learning algorithm itself. It must be set prior to training and remains constant during training. If you set the regularization hyperparameter to a very large value, you will get an almost flat model, a slope close to 0. The learning algorithm would almost certainly not overfit the training data, but will be less likely to find a good solution. Tuning hyperparameters is an important part of building a machine learning system. You will see a detailed example in the next chapter. As you might guess, underfitting is the opposite of overfitting. It occurs when your model is too simple to learn the underlying structure of the data. For example, a linear model of life satisfaction is prone to underfit. Reality is just more complex than the model, so its predictions are bound to be inaccurate, even on the training examples. Here are the main options for fixing this problem. Select a more powerful model with more parameters, feed better features to the learning algorithm, feature engineering, reduce the constraints on the model, for example by reducing the regularization hyperparameter. But now you know a lot about machine learning. However, we went through so many concepts you may be feeling a little lost, so let's step back and look at the big picture. Machine learning is about making machines get better at some task by learning from data instead of having to explicitly code rules. There are many different types of machine learning systems, supervised or not, batch or online, instance-based or model-based. In a machine learning project, you gather data in a training set and you feed the training set to a learning algorithm. If the algorithm is model-based, it tunes some parameters to fit the model to the training set to make good predictions on the training set itself. And then hopefully it will be able to make good predictions on new cases as well. If the algorithm is instance-based, it just learns the examples by heart and generalizes to new instances by using a similarity measure to compare them to the learned instances. A system will not perform well if a training set is too small, or if the data is not representative, is noisy, or is polluted with irrelevant features, garbage in, garbage out. Lastly, your model needs to be neither too simple, in which case it will underfit, nor too complex, in which case it will overfit. There's just one last important topic to cover. Once you have trained a model, you don't want just to hope it generalizes to new cases. You want to evaluate it and fine-tune it if necessary. Let's see how to do that. The only way to know how well a model will generalize to new cases is to actually try it out in new cases. One way to do that is to put your model in production and monitor how well it performs. This works well, but if your model is horribly bad, your users will complain. Not the best idea. A better option is to split your data into two sets, the training set and the test set. As these names imply, you train your model using the training set and you test it using the test set. The error rate on new cases is called the generalization error or our sample error, and by evaluating your model on the test set, you get an estimate of this error. This value tells you how well a model will perform on instances it has never seen before. If the training error is low, your model makes few mistakes in the training set, but the generalization error is high, it means that your model is overfitting the training data. Evaluating the model is simple enough. You just use a test set. But suppose you're hesitating between two types of models, say a linear model and a polynomial model. How can you decide between them? One option is to train both and compare how well they generalize using the test set. Now suppose that the linear model generalizes better, but you want to apply some regularization to avoid overfitting. The question is, how do you choose the value of the regularization hyperparameter? One option is to train 100 different models using 100 different values for this hyperparameter. Suppose you find the best hyperparameter value that produces a model with the lowest generalization error, say just 5% error. You launch this model into production, but unfortunately it does not perform as well as expected and produces 15% errors, which has happened. The problem is that you measure the generalization error multiple times on the test set, and you adapted the model and hyperparameters to produce the best model for that particular set. This means the model is unlikely to perform as well on new data. A common solution to this problem is called holdout validation. You simply hold out part of the training set to evaluate several candidate models and select the best one. The new held out set is called the validation set or the development set or dev set. More specifically, you train multiple models with various hyperparameters on the reduced training set, the full training set minus the validation set, and you select the model that performs best on the validation set. After this holdout validation process, you train the best model on the full training set, including the validation set, and this gives you the final model. Lastly, you evaluate this final model on the test set to get an estimate of the generalization error. This solution usually works quite well. However, if the validation set is too small, then the model evaluations will be imprecise. You may end up selecting a suboptimal model by mistake. Conversely, if the validation set is too large, then the remaining training set will be much smaller than the full training set. Why is this bad? Well, since the final model will be trained on the full training set, it is not ideal to compare candidate models trained on a much smaller training set. It will be like selecting the fastest sprinter to participate in a marathon. One way to solve this problem is to perform repeated cross-validation using many small validation sets. Each model is evaluated once per validation set. It is trained on the test of the data. By averaging out all of the evaluations of a model, you get a much more accurate measure of its performance. There's a drawback, however. The training time is multiplied by the number of validation sets. In some cases, it's easy to get a large amount of data for training, but this data probably won't be perfectly representative of data that will be used in production. For example, suppose you want to create a mobile app to take pictures of flowers and automatically determine the species. You can easily download millions of pictures of flowers on the web, but they won't be perfectly representative of the pictures that will actually be taken using the app for mobile device. Perhaps you only have 1,000 representative pictures actually taken with the app. In this case, the most important rule to remember is that both the validation set and the test set must be as representative as possible of the data you expect to use in production, so they should be composed exclusively of representative pictures. You can shuffle them and put half in the validation set and half in the test set, making sure that null duplicates or near duplicates end up in both sets. After training your model on the web pictures, if you observe that the performance of the model on the validation set is disappointing, you will not know whether this is because your model has overfit the training set, or whether this is just due to the mismatch between the web pictures and the mobile app pictures. One solution is to hold out some of the training pictures from the web in yet another set that Andrew and G dubbed the train depth set. After the model is trained on the training set, not on the trained depth set, you can evaluate it on the trained depth set. If the model performs poorly, then it must have overfit the training set, so you should try to simplify or regularize the model, get more training data, and clean up the training data. But if it performs well on the trained depth set, then you can evaluate the model on the depth set. If it performs poorly, then the problem must be coming from the data mismatch. You can try to tackle this problem by pre-processing the web images to make them look more like the pictures that will be taken by the mobile app, and then retraining the model. Once you have a model that performs well on both the trained depth and the depth set, you can evaluate it one last time on the test set to know how well it's likely to perform in production. In this chapter, we have covered some of the most important concepts of machine learning. In the next chapters, we will dive deeper and write more code, but before we do, make sure you can answer the following questions.